All right, so welcome back to section 5.7, part 2. We're going to take a look at more integration. So here, this is a doozy. My job is to do this integration problem sitting here in front of me. I've got the integral of the fraction. Numerator is 4, denominator is 1 plus the root of 5x dx. Okay. So, I'm just going to start throwing things at the wall and see if something sticks. Let's see. The numerator, the denominator, it doesn't appear that the numerator is the derivative of the denominator, but I see composition downstairs, so I don't know. Last time I saw composition, I did substitution. Let's see if that works. So substitution would say that u is equal to 5x, right? Because that's the inside piece of that composite part. So let's try that. Then du would be 5 dx, or 1/5 du would be dx, and let's try that substitution and see if that works. So I'm going to take this 4 and pull it out in front just to get out of the way. So that's 4 times the integral of, let's see, 1 over 1 plus the square root of u times 1/5 du. Okay. I guess I can take this 1/5 and move it out in front. And so that would give me 4/5 times the integral of 1 over 1 plus the square root of u du. Well, that didn't really help me. I mean, the things that were supposed to happen didn't happen. All the x's went away. That's supposed to happen in substitution. They're replaced with u's, and that's good. But this integrand that I got is not something that I know the antiderivative of. It isn't something easy to integrate. Okay? So that means one of two things. Either substitution is wrong, the wrong technique, or what I chose for my substitution was wrong. All right, so I'm going to erase my work and start over. Okay? Well, if selecting just the inside to be u was wrong, what if we selected the whole piece to be u? What if we said that u was equal to the whole thing, the root of 5x? Let's try that. The other thing didn't work, so I'm trying something new. Then my differential du would be the derivative of that. That would be 1/2 times the quantity 5x to the negative 1/2 times 5 dx. Or if I clean that up a little bit, that's going to give me 5/2 times 1 over the root of 5x dx. Well, I just have dx. I don't have any of this other junk. Every other time when I've had that other junk, I just moved it to the other side. So let's move it to the other side and try and see if that works. So 2/5 times the root of 5x times du is equal to dx, but look right here. 2/5 u du is equal to dx. Let's try that substitution. Okay. So now I'm going to move the 4 out in front. So I've got 4 times the integral. Dx is going to be, let's see, 1 over 1 plus u times dx, which is 2/5 u du. And I kind of ran out of space there. I kind of crammed it in. So let me drag this down and clean it up a little bit. And so that's going to get me, I'm going to take this 2/5 and move it out in front. And I'm going to take this u and put it into the numerator. Okay, so that's going to give me 8/5 times the integral u divided by 1 plus u du. All right. That doesn't look any better because the numerator isn't the derivative of the denominator. The numerator isn't a higher power than the denominator. In fact, the numerator is the exact same power. It's a u to the first and a u to the first downstairs. All right, so ready? Here's a trick. When the numerator and the denominator have the same power, try adding or subtracting a quantity from the numerator to change things up. And here's what I mean by that. I'm going to add 1 and subtract 1 from the numerator, which does not change the value of the expression, but changes so much about this fraction. Because what I'm going to do is I'm going to split this into 2 fractions now. 8/5 is still going to be a coefficient out in front. It's still going to be the integral, but it's going to be a u plus 1 over u plus 1 minus a 1 over a u plus 1 du. Okay, so technically I should have parentheses here. Okay. Now the value of this fraction is going to be a 1, so this is going to turn into 8/5 times the integral of 1 minus 1 over u plus 1 du. Okay. Now I have 2 integrals here. I have the integral of 1 and I have the integral of 1 over u plus 1. So I'm going to rip it apart and write it as 2 integrals. So I've got 8/5 multiplied by the integral of 1 du minus the integral of 1 over u plus 1 du. I don't know what that was, some random stray thing. Okay. This integral I should be able to do, and I think I can figure this one out. Right? Because that looks like a fraction where the numerator is the derivative of the denominator. Right? So my 8/5 drags along. The integral of 1 du is u minus, and over here I'm going to do substitution again. Since I've already used the letter u, I'm going to use the letter v. I'm going to say that v is equal to u plus 1, and then dv is just equal to du, and that turns into the integral of 1 over v dv. This is already done, so it's just going to drag along. So I've got 8/5 times the integral of u minus natural log absolute value v plus c. But this thing is a hot mess because it's got u's, it's got v's, and the original problem had x's in it. So the first thing I'm going to do is I'm going to turn that v back into a u. And so v was equal to u plus 1. So then this becomes 8/5 times u minus the natural log of the absolute value of u plus 1 plus c. Okay. Now I'm going to do a back substitution again. What was u? Oh, way back up here we said u was equal to the root of 5x. So then this becomes 8/5 times the quantity, the root of 5x minus the natural log of the absolute value of the root of 5x plus 1 plus c. Parentheses here to close off those starting parentheses. Now, technically, here, since the square root function has the smallest value of 0 and adding 1 to 0 makes that positive, I could drop those absolute value bars and write this as 8/5 times the root of 5x minus the natural log of the quantity, the root of 5x plus 1 plus c, if you prefer the black line over the blue line. Okay? Now I know what you're thinking. I know you're thinking 2 things about this problem. Oh my gosh, that was so much fun. I love calculus. That was the first thing you were thinking, and I agree, that was fun. And 2, you were thinking, there's no way I would ever have figured that out on my own. And you're probably right. You probably wouldn't have figured that out on your own. Unless you'd seen someone do that trick before, or unless you were willing to spend, 6 or 8, 10 hours just playing around with this thing to try to figure it out, it's nothing that is intuitively obvious. to make it work. Like in this problem that we did, at least it kind of made sense to do long division because, well, the numerator is bigger than the denominator. It's an improper fraction, kind of. So let's make it not look like that. But this one, the U substitution is not obvious because you're not doing what you were taught to do in U substitution. You're not picking the inside piece of the composite function. And then this +1 -1 business that we did right here, where did that come from? Well, the only reason I need to do that is because I'd seen a problem like this before. And when I saw a problem like this before that ended up with this black piece right here, a U over a 1 plus U. And the 1 doesn't matter. The 1 could be anything. Okay? It could have been a 7. And then upstairs, I would have just said U plus 7 minus 7. Or if that 1 downstairs, this 1 right here had been any other number, I would just add and subtract that same other number so that it would end up doing this cancellation that we got. And every single time, the reason that you do that is because this turns into that, and this is big picture. This becomes easy to integrate. Maybe I should say easier. Right? So the expectation is not that you would have come up with this on your own, but now that you've seen it, you could always do it. I don't know if that's a valid expectation or not. I threw in a blank page because I wasn't sure I was going to get that one done in the space provided, so there's an extra page that isn't on yours. Okay? Well, what about using this logic for trigonometric functions? What if my job is to integrate the tangent function? Well, I don't know anything whose derivative is tangent. So it isn't just to undo it by some rule that I memorized. I also don't see composition here, so I don't think this is substitution. So I'm going to go back to a technique that I learned in trig. Whenever I have trig that I don't like, I'm going to rewrite it as other trig that I might like. So I'm going to remember that tangent is just sine x over cosine x dx. And now I see a fraction where the numerator is the derivative of the denominator. I mean, it's missing a negative, but we've learned by now that that can be fixed. So I'm going to say that u is the denominator, cosine x. Then the differential du would be negative sine x dx, or negative 1 times du would be sine x dx. And now I can do my substitutions. Okay? So now I get the integral of 1 over u times negative 1 du. I can pull the negative 1 out in front. It's a coefficient. The integral of 1 over u is the natural log. So I get negative 1 times the natural log of the absolute value of u plus c. But what's still wrong with this? Can't have u, so I get negative 1 times the natural log of the absolute value of u. U was cosine, plus c. Right? Now you will sometimes see people deal with this because remember, a coefficient out in front can be moved up and made into an exponent. And so you'll see sometimes people making use of that here. Right? And they will say, this is the natural log of the absolute value of 1 over cosine, but 1 over cosine is secant. Okay. Now I know what you're thinking. What if cosine was 0? 1 over 0 doesn't work. But the natural log doesn't work with 0. So it's not an issue. Cosine can never be 0 for the natural log function to work to begin with. Right? Cosine can never be 0 because the original function has issues when cosine is 0. Vertical asymptotes of pi over 2 and multiples of pi over 2. Right? Now this exact same logic that we just did right here can be applied to all of the trigonometric functions. You'll notice that for our book, our author has chosen to leave the negative in there as well as the negative here and not moving it up and making it into an exponent. Right? But all of the other 4 trigonometric functions, tangent, cotangent, secant, and cosecant, can all be dealt with much in this way. Right? If you are bored over your holiday break, Try working one of these two out by hand. Okay? I'm going to give you a hint. It's going to require something similar to this to make it work. Something similar to this trick to make it work. So if you're bored, you want to challenge yourself. Those are some fun ones to challenge yourself with. Okay? This brings us to the end of section 5.7. Hope you have a great day.